So I'm going to talk a little bit about electrophoresis, and I want to make sure that I am able to both keep those of you that haven't done it involved, but also those of you that have done it and think you know all about it. Let me make sure that we fill in some gaps. So let's talk now about how we're going to look at this, which is, of course, by electrophoresis. And electrophoresis in general, right, is based on, basically, it's a separation based on charge. Separation based on, I didn't want to say separation, based on the, let's say, the number of charged amino acids. Right? And so it's going to be some function of our lysines, histidines, arginines, aspartates, glutamates. Right? And every protein is going to have some net charge. Right? Plus, 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 minus, 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 depending on the number of positive or negative charges. And so if I now apply an electric field, okay, where I put the plus end of it here and the minus end of it here, right, there's going to be some force on that particle and it's going to move. And the force, as you well know, is just equal to the charge on the molecule. I guess I shouldn't put Q. I'll put Z, where Z is the charge of our protein. Okay? And, which, of course, is simply equal to ma, where a is the acceleration. So now what's going to happen? That particle is going to move faster and faster and faster in that electric field. Okay, except it's going to be opposed by a frictional force. Okay, so the frictional force that's going to oppose the movement, we'll call it F friction, is simply equal to F times V. V is, of course, the velocity here, and F is this frictional coefficient. Now, at equilibrium, once I reach equilibrium, that means, of course, now, that will occur when the net charge on the protein times the electric field is simply balanced by the frictional force that limits how fast we go. And our protein will now move with some constant velocity, v, in that electric field. Okay? So we can say that the speed with which this molecule moves is simply equal to z times the electric field strength divided by F, this frictional coefficient. Now I can do this in solution. I can do it in a gel, something we'll talk about in a minute, that acts as a sieve, right? And if I do this, this is called, if I do it in a gel, this is going to be called native gel electrophoresis. Here's my gel. I can put my proteins up in the top of this gel. It's a 3D structure. I'm only drawing it in 2D because I'm a terrible artist. Okay. And if I apply an electric field, a minus charge here, and a plus charge here, and a minus charge up there, what's going to happen? Well, some of the proteins, if they happen to be negatively charged, are going to move in this direction. But some of the proteins, if they're positively charged, aren't going to move into the gel. They're going to try to move in this direction. Right? So our negatively charged proteins move here. Our positively charged proteins try to move backwards. That's going to be a problem. And furthermore, the amount that my proteins move into this native gel is determined entirely, not just by their charge, but by F, this frictional coefficient. And F depends on the shape. If my protein is perfectly spherical, if it's a big long rod, they're going to move differently in this gel. Okay? So native, this is called, as I said, this is called a native gel. And it's called native because the protein isn't unfolded, right? And clearly, if I do a native gel, I'm going to end up with two problems, right? Proteins moving in opposite directions, right? And proteins whose movement depends on the shape of the protein. Doesn't mean it's a bad technique. People do this technique. It's sometimes useful. But it's not going to be helpful for what we want to talk about, which is purifying proteins from scratch.